There's a moment at every drag strip when the crowd stops talking. When something pulls up that doesn't belong, something that makes people look twice, nudge each other, and quietly wonder if they're about to witness something they'll be telling their grandchildren about. On a warm evening in 1968, at a drag strip outside Mexico City, that something was a Volkswagen Beetle. Canary yellow. Stock body. No spoilers, no hood scoops, no menacing exhaust pipes poking out from anywhere. Just a Beetle. The kind of car your grandmother drove to the market on Sundays. The crowd didn't just laugh, they openly mocked it. Because everyone who knew anything about cars knew what a Beetle could do. 18-second quarter miles on a good day. 0 to 60 in something embarrassing. A top speed that a determined bicycle rider might challenge on a downhill. But then the lights dropped, and the little yellow car launched so hard its front wheels came off the ground. 12 seconds and 8/10 later, it crossed the finish line at 108 miles per hour. The place went completely silent, because what just happened wasn't supposed to be physically possible. And behind it all was a 40-year-old dealership mechanic named Carlos Gonzalez, who had decided calmly, methodically, and without any corporate backing to prove that Germany's most celebrated engineers had fundamentally misunderstood their own creation. This is his story. And it's one of the most extraordinary engineering stories in automotive history. Before we go any further, if you love stories about underdogs, obsessed mechanics, and the kind of innovation that comes not from boardrooms, but from grease-stained workshops at midnight, you're going to want to stick around for this one. This channel is dedicated to exactly those kinds of stories. Subscribe and join us, because we've got a lot more where this came from. Now, let's go back to the beginning, because to understand what Carlos Gonzalez accomplished, you first have to understand just how severely everyone had underestimated what he was working with. The Volkswagen Beetle was never designed to be fast. That wasn't the point. That was never even close to the point. Ferdinand Porsche, yes, that Porsche conceived the original design in the 1930s at the direct request of Adolf Hitler, who wanted a car that ordinary German families could afford. The word Volkswagen translates literally to people's car, and the engineering reflected that mission completely. It needed to be cheap to manufacture, cheap to maintain, and simple enough that a farmer with basic tools could keep one running for decades. The air-cooled, flat-four engine that Porsche designed to power it was a masterpiece of elegant simplicity. No water cooling system meant no radiator, no coolant hoses, no water pump, no freeze plugs. An entire category of potential failures simply didn't exist. The engine hung in the rear, cooled by a belt-driven fan that pushed air across the thin cylinder barrels and heads. It was brilliantly uncomplicated. By 1968, the largest production version of that engine displaced 1,600 cubic centimeters and generated 57 horsepower. To give that number some context, a full-size American muscle car from the same era was pushing between 300 and 450 horsepower from engines 4 times the size. The Beetle's engine wasn't built to compete with those cars. It was built to reliably carry a family to church on Sunday morning and still start faithfully on a cold Tuesday in February. Volkswagen's engineers in Wolfsburg had done their calculations thoroughly and arrived at a set of limitations that they considered absolute. The magnesium alloy crankcase, they determined, could not safely accommodate a crankshaft with more than 1,800 cc of swept displacement without cracking under stress. The cylinder cooling fin arrangement could not dissipate the heat generated by more than roughly 100 horsepower before temperatures entered dangerous territory. Exceed those numbers, and you weren't building a performance engine, you were building a very expensive and very rapid destruction machine. These weren't just conservative guidelines. VW's engineers had the math to back it up, and their math was sound based on everything they'd tested and everything they'd tried. The problem was, Carlos Gonzalez noticed something they hadn't. Carlos Gonzalez had been working as a senior mechanic at Volkswagen de Mexico's primary dealership in Mexico City since the early 1960s. On paper, his job was warranty service and routine maintenance, the kind of work that involves more paperwork than ingenuity. New brake pads, valve adjustments, the occasional gearbox issue. But Gonzalez wasn't content to simply fix what was broken. He was obsessed with understanding things at a level that went well beyond what his job required. Every engine he rebuilt, he studied. Every component he replaced, he measured first. He kept notebooks, detailed, technical notebooks filled with observations, calculations, and questions that nobody else at the dealership was asking. He'd started racing Beetles in 1965, and the experience had turned his obsession into something more focused and urgent. Because racing stripped away all the politeness and civility of everyday driving and asked a single brutally honest question: how fast can this thing actually go? For Gonzalez, the answer was always, not fast enough. The accepted ceiling within Mexico's VW tuning community at the time was roughly 75 to 80 horsepower, and reaching it required exhausting every known trick simultaneously. You bored the cylinders out from 85.5 millimeters to about 88 millimeters, pushing displacement to around 1,700 cc. You hand-ported the cylinder heads to smooth the airflow. You installed an aggressive camshaft. You added dual carburetors. You carefully balanced the rotating assembly. Do all of that perfectly. Spend weeks on it, invest serious money, and maybe you'd see 80 horsepower on a dyno. Push any harder than that, and within minutes the cylinder head temperatures would climb past 400 degrees Fahrenheit. The exhaust valves would begin glowing red. The pistons would seize in their bores. The engine wouldn't just lose power, it would grenade itself spectacularly. So the community had drawn its line. 75 to 80 horsepower. That's the wall. Nobody argued with the wall. Gonzalez looked at the wall and started sketching. Here's the thing about the Volkswagen crankcase that nobody had bothered to fully appreciate. It was overbuilt for what it was being asked to do. When Volkswagen scaled the Beetle engine from the original 1,100cc version up through 1,200, 1,300, and finally 1,600cc, they kept the same basic crankcase architecture throughout. The main bearing saddles, the structural supports that hold the crankshaft in place, were generously dimensioned. The case walls were thick. The overall structure had been designed with far more rigidity than the production engines technically required. Gonzalez recognized this as hidden potential. The case wasn't at its limit. It hadn't even been seriously pushed. The stock VW crankshaft used a 69mm stroke, meaning the connecting rod journals were offset 34.5 millimeters from the main bearing centerline. Gonzalez ran calculations and determined that a crankshaft with an 82mm stroke, 13 millimeters longer, could fit inside the stock crankcase without the connecting rods striking the case walls, provided the counterweights were redesigned to clear the camshaft and oil pump. Paired with cylinder barrels bored to 92 millimeters, this configuration would displace 2,180 cubic centimeters, 2.18 liters, from an engine that Volkswagen had designed as a 1.1. The problem was immediate and obvious. Nobody made that crankshaft. The aftermarket hadn't made it because the aftermarket didn't believe it was worth making. Why engineer components for an engine that couldn't survive using them? So Gonzalez decided to make the crankshaft himself. This is where the story shifts from clever observation to something that genuinely borders on remarkable. Because what Gonzalez did next wasn't just mechanical work. It was precision engineering conducted without a formal engineering education, without a corporate budget, and without anyone else believing it would succeed. He found a machine shop in Mexico City that normally produced components for agricultural equipment, tractors, irrigation pumps, industrial machinery. These were craftsmen who understood metallurgy and precision tolerances, even if they'd never touched an automotive engine. Gonzalez worked with them to design a billet steel crankshaft from scratch. The design challenges were substantial. The counterweights had to be completely reconceived to avoid contact with the camshaft lobe and the oil pump housing during rotation. The connecting rod journals required specialized heat treatment to withstand the increased leverage that the longer stroke would place on them. And the entire assembly had to be dynamically balanced to within half a gram, an extraordinarily tight specification, or the vibration at high RPM would destroy the main bearings within hours. It took 6 months. 14 prototype crankshafts were built, tested, and rejected before the 15th met Gonzalez's standards. Then came the cylinders. The stock VW cylinder was a cast iron sleeve, pressed into an aluminum barrel with cooling fins machined into the exterior. Gonzalez sourced raw cylinder castings and had them bored to his 92mm specification. But he understood immediately that simply enlarging the bore wasn't enough. In fact, it wasn't even close to enough. A bigger engine generates more heat. More heat requires more cooling surface area. The stock 2.4 fin arrangement that worked fine for a 5.7 horsepower engine would be completely inadequate for what he was building. His solution was elegant in its directness. He redesigned the cooling fins entirely. 36 fins per cylinder instead of 24. Each fin machined 2 millimeters deeper than stock. The combined effect was a 40% increase in total cooling surface area per cylinder. It wasn't a dramatic technological leap, it was simply doing more of what already worked, applied with enough mathematical rigor to actually solve the problem. The pistons were custom-forged aluminum pieces with a compression height shortened by 6 mm to accommodate the longer stroke geometry. The wrist pin location had to be moved upward into the oil control ring area, which required sourcing custom piston rings from a racing supplier in California. The compression ratio was deliberately set at a conservative 5:1 mild by performance standards, because Mexican pump fuel in the late 1960s averaged around 80 octane, and Gonzalez wanted an engine that people could actually fuel and drive, not a laboratory curiosity. But none of this would matter without solving the most critical limitation of all: the cylinder heads. A stock Volkswagen cylinder head flowed approximately 65 cubic feet per minute of air at maximum valve lift. That number tells you everything. For comparison, the cylinder heads on a contemporary small-block Chevrolet V8 flowed around 185 CFM. The Beetle head was barely moving a third of the air of an engine it was theoretically trying to compete with. Doubling the displacement of the engine while leaving those heads unchanged would have been pointless. You'd have a bigger engine that still couldn't breathe, like giving someone larger lungs, but keeping the airway the same size. Gonzalez knew this, and he spent more hours on the cylinder heads than on any other single component. He started with bare castings and rebuilt the port geometry from scratch. The intake ports were opened from 28 mm to 35 mm in diameter. The exhaust ports went from 25 mm to 32 mm. But, and this is a critical detail that separates a real engine builder from someone who just makes holes bigger, simply enlarging a port can reduce performance by killing the gas velocity that helps pull the air-fuel mixture into the cylinder. Gonzalez spent hundreds of hours with a die grinder, carefully reshaping the floors and walls of each port to maintain that velocity while simultaneously increasing volume. It's painstaking, intuitive work, and it can't really be taught from a textbook. It has to be felt. The valve guides were narrowed from 11 mm to 8 mm to reduce the obstruction they created in the airstream. The combustion chambers were reshaped to unshroud the valves to remove the cylinder head material that was blocking airflow around the valve edges when they opened. The valves themselves were completely custom. Intake valves grew from 35.5 mm to 42 mm in diameter. Exhaust valves went from 30 mm to 37.5 mm. These were enormous valves for an engine of this architecture, requiring custom valve seats machined from copper beryllium alloy, a material chosen specifically for its ability to transfer heat away from the valve head and into the water jacket. Except, of course, there was no water jacket. This was an air-cooled engine. The heat had to go somewhere else. And ensuring it did required every material and design decision to work together as a system. The valve springs were sourced from Porsche 911 engines and modified to fit. Seat pressure was 120 pounds. At full lift, that climbed to 280 pounds, more than double the stock specification. Then came the camshaft. Gonzalez's custom billet cam had specifications that read like a provocation. Valve lift of 0.56 inches on both intake and exhaust, compared to 0.35 stock. Duration of 296 degrees, the amount of the engine's rotation cycle during which each valve remained open. A lobe separation angle of 108 degrees, which created enough overlap between intake and exhaust events to give the engine that distinctive, lumpy, aggressive idle that you can feel in your chest from 50 feet away. This camshaft required solid lifters with precisely controlled 0.006-inch clearance. And that clearance had to be checked and adjusted every 500 miles, a maintenance requirement that would horrify any modern driver, but was simply an accepted reality of serious performance engines in that era. But here's where Gonzalez made one of his most insightful discoveries. When he carefully measured the rocker arm ratio in the stock VW engine, the mechanical advantage that multiplies cam lobe lift into actual valve lift, he found that Volkswagen claimed a 1-to-1 ratio. But the French intention, actual measured ratio, was closer to 3-to-1, a small discrepancy, but meaningful. By redesigning the rocker shaft position and fitting longer rocker arms, Gonzalez achieved a true 1:4-to-1 ratio. This meant his cams 0. 0.560 inch lobe lift translated to 0.784 inches of actual valve lift at the valve. For an air-cooled flat 4 designed in the 1930s, that number is genuinely extraordinary. In March of 1969, the first complete engine, which Gonzalez rounded up to 2,300 cc from the actual 2,180 cc displacement, partly for the psychological impact of the rounder number fired for the first time on a borrowed engine dyno in a diesel truck shop. The sound it made was wrong, in the best possible way. Every Beetle engine in history had produced that familiar, cheerful, air-cooled clatter, a sound somewhere between a sewing machine and a contented tractor. This engine barked, it snarled. At high RPM, it produced a rising mechanical shriek that made everyone in the shop take an involuntary step backward. First dyno pull, 168 horsepower, at 6,800 revolutions per minute. 3 months of continued development later, after careful tuning of the carburation, ignition timing, and valve events, 203 horsepower at 7,200 revolutions per minute, with 176 pound-feet of torque at 5,500 revolutions per minute. Stop for a moment and let those numbers settle. The stock engine made 57 horsepower. Gonzalez's engine made 203. From the same basic block architecture, the same crankcase, the same fundamental design that Volkswagen had confidently declared incapable of reliable power beyond 100 horsepower. He hadn't just beaten their estimate, he had quadrupled the stock output, naturally aspirated, on pump gasoline. How does something like that happen? How does a dealership mechanic working in a country that German manufacturers barely considered a secondary market outperform the engineers who designed the engine in the first place? The answer says something important about the difference between optimization and exploration. Volkswagen's engineers had optimized the engine brilliantly for mass production, for cost efficiency, for reliability across varied conditions and maintenance standards. Every decision they made was rational within their constraints. But those constraints created blind spots. They'd stopped asking what's possible and started asking only what's necessary. Gonzalez never accepted the first question's boundary. Word of the Mexican Super Beetle reached Wolfsburg quickly, and Volkswagen's reaction was exactly what you'd expect from an engineering organization that had just been publicly embarrassed by one of their own service mechanics. They sent a technical team to investigate. Team's report was unambiguous in its dismissal. The modifications violated fundamental principles of air-cooled engine thermal management. Cylinder head temperatures would inevitably exceed safe operating limits. The crankcase would fracture under the stress of the longer stroke rotating assembly. The main bearings would fail before the engine accumulated 1,000 miles of operation. The project was, in the considered opinion of Volkswagen's engineers, technically incoherent. So Gonzalez invited them to watch a durability test. He installed one of his 2,300 cc engines in a 1967 Beetle, loaded the car with 2 passengers and luggage, and drove it from Mexico City to Acapulco and back. 800 miles of twisting mountain highways in summer heat, exactly the kind of sustained high temperature, high load operation that should have destroyed the engine according to VW's analysis. The car cruised at 75 miles per hour on the highway. On mountain grades that slowed stock Beetles to 35 miles per hour, it climbed without drama. When they returned to Mexico City, Gonzalez pulled the engine apart in front of the German engineers. The bearings showed normal wear patterns. The cylinder head temperatures had never exceeded 380 degrees Fahrenheit within Gonzalez's design parameters. The crankcase was intact. The pistons were clean. The engine looked like it had been out for a Sunday drive. The German engineers left without comment. Racing was always the proving ground. And no car proved the case more dramatically than the one that became a legend throughout Mexican motorsport. Miguel Santana was a racer who understood theater as well as engineering. His car was a 1963 Beetle sedan painted flat matte black with no external modifications whatsoever. No graphics, no racing numbers initially, no aerodynamic additions. It looked exactly like a slightly battered economy car that belonged in a supermarket parking lot. He named it La Cucaracha Negra, the Black Cockroach. At the Autodromo Hermanos Rodriguez, Mexico's premier racing facility, a track that had hosted Formula One events, the Black Cockroach ran quarter miles consistently in the 12.8-second range at 110 miles per hour. To place that in context, a 1970 Plymouth Cuda with the 446-pack engine ran 13.5 seconds, A Boss 302 Mustang ran 14.3. The small yellow car's ugly black cousin was humiliating American muscle cars that cost 5 times as much and produced 4 times the displacement. The psychological impact on spectators who didn't know what they were looking at is difficult to overstate. This was not a modified car that looked modified. It was a stock-appearing Beetle that simply refused to behave like one. People accused Santana of hiding a different engine entirely. Inspections proved otherwise. Everything inside was Gonzalez's work, and it was VW architecture, just reimagined. By 1971, Gonzalez had extracted what he believed was close to the maximum from naturally aspirated development. He'd pushed the architecture as far as atmospheric breathing would allow, so he looked at forced induction, but not in the way you might expect. Turbocharging in 1971 was still primitive technology, unreliable and difficult to package. Gonzalez went a different direction entirely. He sourced a GMC 271 supercharger, a Roots-type positive displacement blower originally designed for use on a diesel bus. The thing was enormous. It was nearly as large as the engine itself and had to be mounted in the space where the rear seat had been, driven by a reinforced belt from the crankshaft pulley. The engineering problems this created were extensive. Positive manifold pressure, the boost produced by the supercharger, completely overwhelmed the stock crankcase ventilation system. Gonzalez designed and fabricated a dry sump oiling system with an external belt-driven pump. The carburetor mounting flanges, which were never designed to handle pressure rather than vacuum, would crack under boost unless replaced with billet aluminum manifolds that Gonzalez machined himself. The engine cooling fan shroud required complete redesign to accommodate the supercharger drive system. With 8 pounds of boost, 315 horsepower. At that point, we have to stop and acknowledge what that number represents. A contemporary Corvette with a 350 cubic inch V8 made around 300 horsepower. A Porsche 911S, the sports car that shared air cooling philosophy with the Beetle, built by a company that had dismissed the Beetle engine as primitive, made 190 horsepower. Gonzalez's supercharged Beetle engine, based on architecture that Ferdinand Porsche had originally designed to move an economy sedan at modest speeds, was outrunning them both. The blown engines required 110 octane racing fuel and needed rebuilding every 2,000 miles. Not a practical street proposition, but in drag racing, where durability is measured in elapsed times rather than miles, they were dominant. Quarter-mile times dropped to 10.9 seconds at 121 miles per hour. In the half-mile, these cars were trapping 145 miles per hour. As Gonzalez's reputation spread beyond Mexico's borders, Volkswagen escalated from engineering skepticism to legal threats. In 1972, VW Mexico delivered a cease and desist letter alleging patent violations and reputational damage. Gonzalez's attorney sent back one simple question: which patents, specifically, were being violated? The answer was none. The stroker crankshaft was Gonzalez's original design. The modified cylinder heads were his work performed on raw castings. The forced induction system used no Volkswagen components. There was nothing to litigate. VW quietly withdrew the threat and never raised it again. But here's the detail about Gonzalez that elevates him from impressive mechanic to something more philosophically interesting. He never patented any of his own designs either. When asked why not, he said simply that knowledge should be free. That if Volkswagen had shared their engineering data openly, he might not have needed to figure things out himself. He chose not to replicate their proprietary approach. In practice, this meant that his specifications circulated through the enthusiast community freely through letters, through classified advertisements in VW magazines, through word of mouth at race events. By 1973, he was shipping complete stroker kits internationally. The moment that legitimized Gonzalez's work in the eyes of the North American enthusiast community came when Gene Berg, a name that carries real weight in VW performance circles, a man who had been building and racing VW engines for 15 years and considered himself to have a comprehensive understanding of what the platform could do, ordered one of Gonzalez's kits. Berg assembled it with methodical precision of a man who expected to be disappointed and wanted documentation of exactly how it failed. He measured every clearance, recorded every specification, approached the whole exercise as a technical investigation rather than a build. On his dyno, 198 horsepower at 7,100 revolutions per minute. Berg ordered 10 more kits immediately. Within a year, Gonzalez specification engines were dominating West Coast VW drag racing. The community that had defined the platform's performance ceiling for over a decade had its ceiling removed by a mechanic from Mexico City who'd never been to California. One of the most unexpected dimensions of Gonzalez's story involves aviation, a world where the consequences of engine failure are considerably more severe than at the drag strip. In 1979, an experimental aircraft builder named William Wynn came to Gonzalez with an unusual brief. He wanted to power a home-built airplane with a Volkswagen engine, but he needed absolute, documented, proven reliability. Aircraft engines don't get second chances. Wynn had heard that Gonzalez's engines had survived tests that destroyed factory units. He wanted to know if that reliability could be engineered into a version suitable for flight. Gonzalez developed a dedicated aircraft variant of the 2,000 300cc engine. Compression was dropped to 5-to-1 for operation on aviation gasoline. The camshaft was replaced with a milder grind, using hydraulic lifters to eliminate the constant adjustment requirement. Dual ignition systems, 2 spark plugs per cylinder, 2 independent ignition systems, provided the redundancy that flight demands. An 8-quart deep sump oil system replaced the stock 5-quart setup. Every single component was MagnaFlux crack-tested before installation. The resulting engine was derated to 125 horsepower conservative by Gonzalez's standards. The resulting engine was derated to 125 horsepower conservative by Gonzalez's standards, but chosen for unlimited reliability rather than peak output. Even at that power level, it transformed VW-powered aircraft, where the 1,600cc factory engine had struggled to climb on hot days. The 2,300cc aircraft engine climbed at 1,200 feet per minute. Wynn's prototype flew from Florida to Alaska and back approximately 8,000 miles with no maintenance beyond oil changes. The FAA declined to certify the modifications for production aircraft. But for experimental category homebuilds, where the builder accepts full responsibility, the Gonzalez engine became the standard. Today, hundreds of aircraft fly on engines derived from his designs, accumulating flight hours with safety records that rival certified power plants. In 1982, a racer named Juan Pablo Montoya, father of the Formula One driver who would later bear the same name, built what remains the most extreme expression of Gonzalez's engineering philosophy. A Beetle dragster, fitted with 2 supercharged 2,300cc Gonzalez engines, coupled together. Combined output, 640 horsepower. Quarter-mile time, 8.7 seconds at 154 miles per hour. The engineering required to make 2 air-cooled engines function as a single powertrain was staggering. The crankshafts had to be phased precisely 180 degrees apart for rotational balance. The superchargers were synchronized through a jackshaft. 8 Weber carburetors fed by 4 mechanical fuel pumps handled the fuel delivery. Heat management, always the central challenge of air-cooled performance, was addressed with NACA ducts cut into the body and supplemental electric cooling fans. The engines needed complete rebuilds every 26 passes. Nobody complained. Meanwhile, Gonzalez himself was pursuing a different direction. In 1983, he developed a 2,100cc street variant, 78mm stroke, 90mm bore that produced 110 horsepower on regular pump gasoline, with hydraulic lifters and a conservative cam profile. These engines would run 100,000 miles between rebuilds. They were what Gonzalez had originally hoped to build, not race engines that happened to be installed in streetcars, but genuinely usable performance engines that ordinary drivers could rely on. By 1985, Gonzalez's company Mexibug Performance employed 42 people and was producing 500 complete engines and 2,000 stroker kits annually. The Mexican government awarded him the National Prize for Technological Innovation, and then Volkswagen did something that represents, perhaps, the most complete possible acknowledgement that they had been wrong. They hired him. In 1986, Gonzalez traveled to Wolfsburg as a special advisor for alternative engine development. His official brief was broad and deliberately vague. His actual function was to teach the engineers who had dismissed his work as impossible how he had done it and what they had missed about the engine they had designed. The lessons he brought influenced the development of later VW engines, though the company never publicly acknowledged the connection. A former Porsche engineer speaking in a 1998 interview was more candid. "The work from Mexico," he said, had revealed possibilities that the factory had not considered. That admission, offered quietly decades after the fact, might be the most significant sentence in this entire story. What Carlos Gonzalez proved wasn't simply that you could extract more power from a Volkswagen engine. That's interesting, but it's not the point. What he proved is something more fundamental and more broadly applicable. He proved that the limits manufacturers publish are not laws of physics. They are engineering decisions, conservative ones, shaped by production economics, legal liability concerns, warranty obligations, and assumptions about how their customers will use their products. Within those constraints, the decisions are rational, but the constraints themselves are chosen, not discovered. Volkswagen had tested extensively within a defined parameter space and found limits. Gonzalez asked what happened outside that parameter space and found that the walls weren't walls at all. The crankcase that couldn't handle more than 1,800 cc has since accommodated 2,100 cc, 2,300 cc, and eventually 3,000 cc in high-performance applications. The architecture that couldn't cool more than 100 horsepower has run reliably at more than twice that with modified cooling geometry. Every limit that Wolfsburg published turned out to be a description of what they had chosen to build, not a description of what was possible. Think about what that means. Every time an engineer or a manufacturer tells you something can't be done, it's worth asking, can't or just hasn't been yet? Carlos Gonzalez is 91 years old. He still lives in Mexico City. His workshop closed in 2001. But he still consults for racing teams and aircraft builders who seek him out specifically because of what he accomplished half a century ago. A documented Gonzalez-built 2,300 cc engine from the 1970s sells today for between $15,000 and $20,000. La Cucaracha Negra, Miguel Santana's famous flat black Beetle, sold at auction in 2018 for $340,000. The modern VW drag racing engines that trace their philosophical lineage directly to Gonzalez's work now displace 3 liters, use turbocharging, and produce over 1,000 horsepower from the same basic crankcase architecture that Volkswagen designed in the 1930s to make 25 horsepower. When Gonzalez is asked what he considers his greatest achievement, he doesn't talk about dyno numbers, or elapsed times, or the validation of being hired by the company that once tried to sue him. He talks about the letters. The teenager in Brazil who built his first race engine from translated articles about Gonzalez's techniques. The aircraft builder in Australia, whose engine has accumulated 3,000 flight hours without failure. The mechanic in the Philippines, who used Gonzalez's porting principles to build something nobody around him believed was possible. Because that's the real legacy, not the 203 horsepower, not the 12.8 second quarter mile, not even the supercharged monster that embarrassed Corvettes. The real legacy is the idea that engineering authority doesn't belong only to institutions. That the person closest to the material, the one who spends years listening to engines, feeling their feedback, understanding their character, sometimes knows things that the people who designed them don't. Carlos Gonzalez didn't just build a fast Beetle. He demonstrated that curiosity, combined with rigor and persistence, is more powerful than credentials, and that the most important question an engineer can ask is the one everyone else stopped asking. But what if we tried this? The Volkswagen Beetle was designed to be the people's car. Affordable, humble, reliable. Carlos Gonzalez looked at that humble little car and saw something that its creators had overlooked entirely. He saw potential. And then he spent the better part of his life proving it was there all along. What other examples do you know of where someone outside the mainstream, a self-taught engineer, an independent builder, an outsider to an industry, discovered something the experts had completely missed? Leave it in the comments. Those are the stories worth telling.